Section 1.1 is on systems of linear equations. And a linear equation includes the variables x sub 1 up through x sub n, where it's written as an equation such as a sub 1 times x sub 1 plus a sub 2 times x sub 2 all the way up to a sub n times x sub n is equal to b, with the coefficients of a sub 1 up through a sub n and b. These could be either real or complex. In this class will be, I believe, for the most part, dealing with real entries as opposed to complex or imaginary. And n is any positive number. And an example of a linear equation is 2 times x sub 1 minus 3 times x sub 2 is equal to 9. Despite the fact that we have two x's in this, with just different indices on it, this is the same idea, for example, when we would have a regular equation such as 2x minus 3y is equal to 9. Both of them mean the same thing. This top one, though, just has a different index for both of these x variables, just to show that they're two different variables, as opposed to introducing a y. An example of a nonlinear equation is 4 times x sub 1 plus x sub 2 is equal to x sub 1 times x sub 2. But the whole point of this particular class of linear algebra, we will mostly be dealing with these linear equations. And a system of linear equations, or linear system, is one or more linear equations involving the same variables, x sub 1 up through x sub n. So, for example, 2 times x sub 1 plus 3 times x sub 2 plus x sub 3 is equal to 4, and x sub 1 minus x sub 2 plus 5x sub 3 is equal to 10. This particular linear system that we have here is not a typical one that we'll be seeing, but this certainly is indeed an example of one. A solution is a list of values s sub 1 up through s sub n that make a linear system true when you substitute those values in respectively into the equations. So, meaning s sub 1 goes in for x sub 1, s sub 2 for x sub 2, and so on. The solution set is the set of all possible solutions. Sometimes this will be only one, sometimes it will be many. It depends on the example that we're talking about. And linear systems are equivalent if they have the same solution set. The types of solutions that we can have, and I kind of glossed over this, we can have exactly one. So that's where all the lines, depending on how many equations we have and how many variables. But if the equations, the lines that make up the equations, if they intersect at exactly one point, that is a good, valid type of solution set. We just have only one point, such as in this example here. Or we can have infinitely many, meaning that the lines lie on top of each other. They're the same exact line. Maybe just a multiple of each other, but they're the same line. So that's infinitely many. If we have either exactly one or infinitely many solutions, both of those are considered consistent systems, meaning that both of them have a point or points, respectively, where they make sense. A no solution or inconsistent equation is where we have parallel lines. They have the same slope, just different y-intercepts, different parts where they cross the x-axis, and as such, they never intersect, so they don't have any solution. Aside from being no solution with the parallel lines, they're also inconsistent because they don't actually intersect at all. And when it comes to our linear systems, we can write these using a matrix. And a matrix is just a fancy schmancy terminology for a rectangular array. So, a matrix using that rectangular array, we have a type of matrix as a coefficient matrix, or a matrix of coefficients. That's where the coefficients from the linear system are written in a matrix in order. An augmented matrix adds an extra column to the coefficient matrix with the constants after the equal sign, such as this matrix down here is an example of an augmented matrix. The size of a matrix, denoted by m by n. M is the number of rows and n is the number of columns. So, for example, this system I have down here, x sub 1 plus 2x sub 2 minus x sub 3 is equal to 9. That's written in this augmented matrix as 1, 2, negative 1, 9, based on the coefficients and the constant. The second equation, x sub 2 plus 8x sub 3 is equal to 2. This gives us, for this row, 0, 1, 8, 2. And then 2x sub 1 plus 5x sub 3 is equal to 0. This is written as 2, 0, 5, 0. Alright. And in our example here, we have 3 variables and 3 equations. Here we have 3 rows to match the number of equations, and 3 columns to match the number of variables. So this is an example of a 3 by 3 matrix. Now we could write this as an augmented matrix just the way it is, or the other way we could write this, and especially if you look at any other linear algebra textbooks, some of them do this, which is why I want to show it to you very quickly. Let me just rewrite out these other columns before continuing on with it. Alright, one of the ways to write the augmented matrix is the way I have it written here. Only problem with this is that if you just look at this without knowing that this last column is the solution set, or the solution from each of these 3 equations, if you don't automatically know that, you might accidentally get confused with regards to the calculations with regards to it. This is why some textbooks put a line to separate the coefficient matrix from those solutions, from those constants. Either way of these is fine. Just be aware though, if you use this original method, that this additional, and let me just get a highlighter up on this, this additional column right here, this column is those constants after the equations, which is why we can't do whatever math that we do to that particular column. Well, I mean, we do some math to it, but not some of the specific things that we'll be doing to the coefficients. So for example of solving a linear system, let's take this 3 by 3 linear system here. X sub 1 minus 2x sub 2 plus x sub 3 is equal to 0. 2x sub 2 minus 8x sub 3 is equal to 8. And 5x sub 1 minus 5x sub 3 is equal to 10. Written as a matrix, this 3 by 3 system looks like this. 1, negative 2, 1, 0, 0, 2, negative 8, 8, 5, 0, negative 5, and 10. Now, going from this matrix to the one here to the right, okay, we need to do something here. Because when we solve a linear system, and, if we had them out as equations and tried to do them, if you ever try to use it with three equations and 3 variables, it can get a little messy. But the way that we normally would solve these, specifically, we need to get a total of 3 zeros. And in our equation here, we already have a 0 in one of the positions. This one right here. That one already has a 0. Normally, if we started to solve these, we would first need to get a 0 there. There's already a 0 there, so we don't care about that one now. Now we need to get a 0, and let me just use a different color to highlight the fact that we are referring to a different location. We want to make this 5 right here to be a 0. Alright. And then the question from that then becomes, how on earth are we going to make that 5 be a 0? Well, from our first row, we have a 1 here, and we have a 5 here. In order to make this 5 here be a 0, we could take this first row, multiply it by a negative 5, and add it to this third row, which will then make this 5 be a 0. So we are taking negative 5 times the first row and adding it to the third row. And this is going to replace the third row. So the first two rows in here are going to look exactly the same because we didn't touch them. We have 1, negative 2, 1, 0, 0, 2, negative 8, 8. Now this bottom row now becomes 0, 10, negative 10, 10. After we multiplied all these by negative 5 and added them down. So 1 times negative 5 made negative 5 plus 5 makes this 0. Negative 2 times negative 5 is positive 10 plus 0 makes positive 10. 1 times negative 5 minus 5, that makes negative 10. And then 0 times negative 5 plus 10 also makes 10. So that's how we got this bottom row. So now we have a 0 here and a 0 here. The last part that we need to do, since this is indeed a 3 by 3 matrix, last thing we need to do is make, and let me actually use a different color just to color coordinate this a little bit. We want to make this 10 right here be a 0. Now you might have noticed previously it was a 0. Now it's not. We need to make that be a 0 again. Again, this is due to the fact that this is indeed a 3 by 3 matrix. So how do we make this be a 10? Well, if we look at the row right above it, which already has a 0 here, right? We don't want to use the first row again, because then now put another number here. And we'll just go back to a different equation, and it's not going to make much sense. We need to use this second row. And since this is a 10, if we multiply this 2 right here by a 5, a negative 5 specifically, and add it to 10, we get a 0. So for the third row, we are going to take negative 5 times the second row and add it to the third row. And not with a 5 in there. Excuse me. We're just adding it to the third row. So negative 5 times the second row plus the third row. This gives us, again, the first two rows here are not going to change. 1, negative 2, 1, 0, 0, 2, negative 8, 8. Now, because we're doing negative 5 times the second row and adding it to the third row, we have 2 times negative 5 plus 10, that makes it a 0. Negative 8 times negative 5 plus negative 10, that makes 30. And then negative 5 times 8 plus 10, this gives us negative 30. Now you might see a slight little bit of an issue here. This row here has all multiples of 2, and this row here has multiples of 30. So we could simplify this a little bit. We could divide this row here in half to get rid of this 2 and make it be a 1, just write this entry right here. So we're going to take 1/2 and multiply it by the second row. And in this bottom row, we have 30s. Again, to make this 30 here be a 1, we can multiply that third row by 1/30th. Okay? And doing so now is going to make this matrix down here 1, -2, 1, 0, 0, 1, -4, 4 when we divide this row in half. And then dividing this row by 30, we get 0, 0, 1, -1. And now we can write these as equations. So the three equations that we have, and I kind of wish that last one did not go in the middle there. But x sub 1 minus 2x sub 2 plus x sub 3 is equal to 0. X sub 2 minus 4x sub 3 is equal to 4. And x sub 3 is equal to -1. That's just writing this matrix back as a linear system. Now, since x sub 3 is already equal to -1, we can leave that up the way it is. And we're going to proceed upwards, going from bottom to top here. So since x sub 3 is equal to -1, that we could just keep as is. We could take this middle equation here now and solve for x sub 2 by adding 4x sub 3 over. So x sub 2 is equal to 4 plus 4 times x sub 3. -1 was x sub 3. So this is going to make us, and this is supposed to be an x and -1 here, not a -2. Let me just very quickly change that. This is supposed to be a -1. So 4 plus 4 times -1, this just makes 0. So x sub 2 is 0. And then for the top equation, we could solve this one for x sub 1. This will be x sub 1 is equal to 2 times x sub 2 minus x sub 3. This makes 2 times 0 minus -1. This gives us a positive 1. So the solution that we get for this is the point 1, 0, -1, due to the values we got when we solved this. And this particular example is referred to as a consistent linear system. Consistent. And we kind of did this without really explaining out the steps per se in this way. But we would use elementary row operations when solving that matrix. So I didn't do the first one, but it's still an option. It's where we replace a row. So replacement, we replace one row by the sum of itself and a multiple of another row. We actually did that one multiple times, as you saw. We did not interchange rows. That's where we switch to rows. That doesn't really impact much, but it does allow us to move a 0 if we wanted to. And then scaling, multiply all entries in a row by a non-zero coefficient. This does not have to be a whole number, which is why you would notice I used fractions down over here. And a matrix is row equivalent where a sequence of elementary row operations transforms a matrix into another. Augmented matrices share the same solution set. So all that basically means is, in this example, this first matrix has the same solution set as this one, and this one. Which is why we could do these and actually still get the same answer. And when it comes to a solution set from these linear systems and matrices, we have the idea of existence and uniqueness to think about. So this is to determine why a linear system contains no solution, exactly one solution, or infinitely many solutions. And we ask ourselves, is this system consistent, like my previous example? where at least one solution exists. And if the solution does indeed exist, is it the unique or only solution? In the example we did before, that was indeed a unique solution, right? We only had one. So yes, it existed and was unique. But that's not necessarily always the case. So do bear that in mind. And we can ask ourselves, are linear systems consistent, such as this one? X sub 2 minus 4x sub 3 is equal to 8. 2x sub 1 minus 3x sub 2 plus 2x sub 3 is equal to 1. And 4x sub 1 minus 8x sub 2 plus 12x sub 3 is equal to 1. We could write this as a linear system. 0, 1, negative 4, 8. 2, negative 3, 2, 1. 4, negative 8, 12, 1. Now in this instance, we're first going to take these two rows, row 1 and row 2, and interchange them. Doing so is going to produce this matrix: 2, negative 3, 2, 1, 0, 1, negative 4, 8, 4, negative 8, 12, 1. Now to move to this next matrix, we want to make, and I'll color code this again, we already have a 0 in this spot. We want to make this 4 right here be a 0. And so, how are we going to do that? Well, looking at this first row, if we multiply by a negative 2, we get negative 4 here, and we'll be able to make a 0 where this 4 here is. So we are going to take negative 4 times the first row and add it to the third row. And again, that's going to replace our third row. So the first two rows stay the same: 2, negative 3, 2, 1, 0, 1, negative 4, 8. Now, when we multiply this first row by negative 4 and add it to the bottom row, we get 0, negative 2, 8, negative 1. And now, we want to make, well, I shouldn't say make per se, we want to change this negative 2 and make that be a 0, just as we did with the 4. So changing this to be a negative 2. In order to do that, we look at the second row here, and if we multiply the second row by a 2 and add it to the third row, this negative 2 becomes a 0. So 2 times the second row, and we add it to the third row. Again, that replaces the third row. So 2, negative 3, 2, 1 for the first row, that stays the same. 0, 1, negative 4, 8 for the second row, also stays the same. But now when we multiply the second row by 2, add it to the third row, we get 0, 0, 0, 15. And we can rewrite this out. We get 2x sub 1 minus 3x sub 2 plus 2x sub 3 is equal to 1. X sub 2 minus 4x sub 3 is equal to 8. And then 0 is equal to 15. By just looking at that, this last equation here makes absolutely no sense. 0 and 15 are not the same number. So because of that, this is an inconsistent system. And we will see later in one of the upcoming sections that this particular system has special functionality in it. And I should also probably note one more additional thing. When we finish this performing those elementary row operations in a matrix, when we have a matrix in a form such as this one, where these three values here are zeros. A matrix where those three values there are zeros. A matrix such as that is a matrix in the upper triangular form. All that means is the numbers above these two zeros. So all of the, well, this particular example has a zero here too, but normally there's a number there. That would be an example of an upper triangular form. So we'll just these three entries here are zeros. Let me know if you have any questions or concerns. Thank you.